Okay, last class we finished up section 6.11 that dealt with carbocation rearrangements. Now we're on to the very last section of chapter 6, section 6.12, which deals with reversible and irreversible arrows. So when we're talking about an irreversible arrow, that's an arrow just going in one direction. And when we're talking about reversible, we write our arrows like this. Notice reversible arrows, if you draw it like this, that is a big no-no. Okay, that's wrong because this is a resonance arrow, resonance, and you want to use the appropriate arrows at the appropriate time. But let's take a look at this mechanism on this slide. It says some reactions like this one here are drawn as equilibria, right? We have a reversible arrow, so that indicates that we're in equilibrium here. Whereas others are drawn as irreversible. And if you look at this reaction, well, there's just an arrow going in one direction. So they're saying this is irreversible. Okay, well, how do we know when to put which arrow? And the question of reversibility is both a kinetic and thermodynamic question, which is good because we've been talking about kinetics and thermodynamics in this chapter. However, Dr. Klein has found a way, I think, to really lay out some rules here that make this pretty reasonable. So let's take a look. It says, if the attacking nucleophile, so talking about nucleophiles, if you have a nucleophilic attack, which we see here, you've got a nucleophile, you've got an electrophile, so we would call this an Na, which stands for nucleophilic attack. If this nucleophile is also a good leaving group, it's going to be a reversible attack. Well, I've told you a few times that water is a good leaving group. Okay, so H2O is a good leaving group, and that's why this is reversible. Now, if you want to know, well, how will I know that something is a good leaving group? Do I just memorize all the good leaving groups? No need to do that. A good leaving group is defined as this. A good leaving group will be the conjugate base of a strong acid. And what do you mean by strong acid, Mr. Dion? I mean something with a pKa, put a pKa less than 0. Okay? So if we think about hydronium, hydronium has a pKa of what? This is something you should have memorized earlier on in the class. It has a pKa of negative 1.7, which is less than 0. Therefore, its conjugate base, after it loses a proton, is water. So that means that water is a dandy leaving group. It's a great leaving group. If you're wondering, could you give me a list of some others? Well, let's think about the strong acid. So H3O plus is a strong acid. So water would be a good leaving group. What's another strong acid? What about HI, HBr, and HCl? Those are all strong acids. That means that I minus, or the iodide ion, the bromide ion, the chloride ion, those are the conjugate bases of hydroiodic acid, hydrobromic acid, and hydrochloric acid, respectively. So those would all be good leaving groups. And we're going to see some others as well, but let's just stick with these ones for now. And we're actually going to see some others probably today when we get into chapter 7. So that would be some good leaving groups. So it says the reverse process, where the leaving group just leaves, like it's shown here, occurs at an appreciable rate. So now you know what a good leaving group is. And if your nucleophile is also a good leaving group, it's going to be a reversible nucleophilic attack. Okay, what else? If the nucleophile, however, is a poor leaving group, it's going to be essentially an irreversible attack. So let's say we have this ketone here. We know that the carbonyl has an electrophilic carbon. We know that this carbon is delta plus. We have a nucleophile. It's got a negative charge right on it. We have our nucleophilic attack occurring here. And it says this is irreversible. Why? Because this is a bad leaving group. Now, if a good leaving group was the conjugate base of a strong acid, a bad leaving group is going to be the conjugate base of a weak acid. Well, let's think about CH3 minus. That's the conjugate base of what? It's the conjugate base of methane, CH4, which is an alkane, and alkanes have a pK of around 50. That's about as weak an acid as you can possibly get. So if this is such a weak acid, that means that this is a strong base, and it is going to be a terrible, terrible leaving group. It's the conjugate base of a weak acid. The reverse reaction doesn't happen. So we're never going to see CH3 minus acting as a leaving group. If you just want to think about it from the point of view of good leaving groups, that'll work too. You could just say to yourself, Well, CH3 minus is not the conjugate base of any of the strong acids I know. Therefore, it's not going to be a good leaving group. That works too. There we go. So that talks about, or so, we've dealt with nucleophilic attacks. There we go. Let's move on from nucleophilic attack to the loss of a leaving group. How do we know if that's reversible or irreversible? Well, it's pretty quick. If you read this first point, it says the loss of a leaving group. So whenever you have an LLG, it's pretty much always reversible. The leaving groups that we encounter can act as nucleophiles. And again, I already went over a little bit about good and bad leaving groups. Sorry, I'm getting ahead of myself here. We were talking about, we were talking about good leaving groups here, so I'm not getting that far ahead of myself. Anyhow, we were talking about good and bad leaving groups already, and we're going to talk about this in even more depth in Chapter 7. So a weak base, or the conjugate base of a strong acid, is a good leaving group, and strong bases are poor leaving groups. So again, this is just a different way of thinking about what I said. So a weak base is a good leaving group. Well, a weak base is the conjugate base of a strong acid. But the bottom line is any loss of leaving group is pretty much going to be reversible. And that brings us to the last one, which is the proton transfer. We have rearrangements too, but here we have the proton transfer. And this is all proton transfers are technically reversible. I would say are technically reversible, but we're going to see many situations where a proton transfer is not reversible. It's irreversible. So here's the rule. If you have a pK difference of 10 units or more, it's pretty much considered to be irreversible, right? If you take a look at the acid here, which is water, and you take a look at the acid over here, the conjugate acid on the other side, we see that we have a difference of 34 pK units. So that is such a big difference that the equilibrium is going to lie completely to this side. There'll be virtually none of these things over here. So that's essentially irreversible. But if you look at your acid and your conjugate acid, like here, we see we have a very small difference in pK. It's around 2.3. Therefore, we consider that to be irreversible. Okay, so that's the rule of thumb. There are, exceptions to this rule probably, but I won't be asking you about any of those at any point in this course, so don't worry about that. And the last one that I kind of forgot was the carbocation rearrangement. Well, let me tell you right now, a carbocation rearrangement, anyone that we're going to see in this class is going to be irreversible. It says generally, but in Chemistry 3101, everything is going to be irreversible. Because you think about it, what's happening? You're taking something that's less stable, like this secondary carbocation, and you're making something that's more stable. If it's more thermodynamically stable, then why the heck would it go backwards to make something that's less stable? That's an uphill climb in energy, and therefore it's not going to happen. So that summarizes everything you need to know about reversible and reversible arrows, but you can imagine that organic chemistry will always come at you with some kind of exception. It says here, and I wouldn't really call this an exception, actually. I would just say that this is a consideration you need to take into account. Do you guys remember Le Chatelier's principle? Would have covered this in General Chemistry 1. Some people even look at this in high school chemistry. Le Chatelier's principle just means if you have something that's in equilibrium, if you have some kind of process that's in equilibrium, and you disturb that equilibrium, the system is going to react in such a way that it's going to try to restore that equilibrium. That's all it is. And so if you have a reaction like this, and this isn't a reaction that we specifically look at, excuse me, in this class, this is part of the mechanism of a reduction called a Wolff-Kishner reduction. You could Google it if you wanted to. This is called the Wolff-Kishner. The Wolff-Kishner reduction is what you call this. Again, you could look it up on Wikipedia even. I'm sure it would be on there. Anyhow, but we lose nitrogen gas, right? You should remember from Gen Chem that N2 is a gas. And what's going to happen if you make a gas in your reaction? It's just going to end up as bubbles, and it's going to go whoop out of the out into the atmosphere. Well, that's not coming back. So there's no way for this to go backwards. All right. So, if you have a gas that's definitely, formed, that's going to escape the reaction vessel, and therefore it's impossible for it to go in the reverse direction. So let's just kind of review quickly. We'll go back to the top here. Take a quick peek at it. So we started here We have reversible, irreversible arrows. We want to decide which one to use in our mechanisms. And first, we started with the nucleophilic attack. We said if it's a good leaving group, it's reversible. If the nucleophile is a crummy leaving group, it's irreversible. Then we said the loss of leaving group is pretty much always reversible. What else? Then we said proton transfers. If the pK difference of the acid and the conjugate acid is greater than 10, it's irreversible. If it's less than 10, it's reversible. That's just a rule of thumb that we use. And then lastly, for the carbocation rearrangements, those are pretty much irreversible. I don't think we'd see any cases where that would be reversible. Well, now we're going to go back even further in the recesses of our minds and the lecture notes. I just want to remind you of something here. So we're going to kind of go back to section 6.8. So I'm going all the way back here. And we talked about the 4 types of mechanisms that you need to know in this class. So the nucleophilic attack, the loss of leaving group, the proton transfer, and the rearrangements. And what we're going to do now is we're going to take a look at some practice problems from the textbook, and we're going to put all of these mechanisms into practice. And what I can tell you is this, is that I've taught this class many, many times. And whenever I teach this class, I'll always print out this sheet. And obviously I posted it to Canvas for a class here. Where was it? Chapter 6 practice problems right here. Okay, so I always print this out or I post it as a PDF for my students, and then we start going over this. And this is where I see, people will sometimes, begin to find organic chemistry very difficult because, they're finding getting the curved arrows challenging. So what I can tell you is this, is if you find curved arrows difficult, what are your options? Your best option is to practice them. You can go and seek out other YouTube channels and other videos, and that's a good idea. However, and you've heard me say this 100 times, it's drawing curved arrows is akin to riding a bicycle. It cannot be learned by watching it. You've got to grab a pencil and a piece of paper and try it yourself in order to get the hang of it. There's no amount of watching somebody. Can you learn something from watching? Sure. But most of what you're going to learn is from trying it yourself. So let's start with this first reaction here. We can see that this is in equilibrium, which is neither here nor there. We're just worried about drawing the curved arrows. But what's happening here is that we're going from this compound, excuse me, where we have a nitrogen that's got 3 bonds, 1 lone pair, therefore it has no formal charge, excuse me, to a nitrogen with 4 bonds and no lone pairs, therefore it has a +1 charge. Could anybody tell me what's happening here? Is this a nucleophilic attack, a proton transfer, a loss of leaving group, or a carbocation rearrangement? And this first step right here. Absolutely, Clinton. Thank you very much. That is a proton transfer. How do I know? A proton was transferred from here onto here, and then it is shown here in this product. So how do we draw the curved arrow? You've got to know how to draw the curved arrow correctly. Remember that a curved arrow always starts with its tail either on a bond or on a pair of electrons. Well, if we're making this bond right here, where did that pair of electrons come from? It came from this pair right here. Notice that the oxygen in hydronium only has 1 lone pair, but over here it's got 2 lone pairs. So where did that lone pair, that extra lone pair, come from? Well, this is where it came from. Let's do the curved arrow. We're going to start with the tail of the arrow on the lone pair, and we're going to grab this proton. All right, well, this proton, a hydrogen atom, can only ever have 1 bond. That means that this bond needs to break, and the pair of electrons is going to end up on the oxygen so that we have 2 lone pairs in our water molecule. There's the proton transfer. Any questions about that one? About that first step? Don't hesitate to interrupt me at any time. You cannot offend me by doing that. In fact, I enjoy answering questions about organic chemistry. Okay, cool. Let's try the next one. Ooh, next one's kind of interesting. It's another step that's in equilibrium. And we're starting out with this compound, and we're treating it with water. And you see that we're making a new carbon-oxygen bond between this carbon and the oxygen of the water molecule. So our new bond is right here. It's this bond right here. Could anybody tell me, would this be a rearrangement, loss of leaving group, proton transfer? what have you. Could anybody tell me which mechanism is being demonstrated here? Yes, absolutely. Thanks, Kiana. It's a nucleophilic attack, isn't it? Right? Water is acting as a nucleophile. And the reason this is reversible is because I told you that water is also a good leaving group. It's the conjugate base of a strong acid. And so where's our electrophilic center? Well, this carbon is highly electrophilic, right? You could draw a resonance structure where you actually show a carbocation. It's not asking us to do this, but I'll just show you very quickly. You could draw this resonance structure like this, where you have the positive charge right on the carbon. So this carbon is highly electrophilic. It wants to undergo a nucleophilic attack. So let me just erase this. There we go. Excuse me. There we go. All right. So what's our nucleophilic attack going to look like? Could anybody tell me where the tail of my arrow would start? Where the tail of my arrow start? Yes. Thanks, Nicole. Absolutely. On the lone pair of the oxygen. That's right. So it's going to start here. There's my nucleophilic attack right here. But if I was to just draw that arrow alone, that's not correct because carbon cannot have 5 bonds. This is a new bond that's being formed. But now the nitrogen has to have a lone pair. It's going to take this pair of electrons from the pi bond, and we're going to put them on the nitrogen. So this is a nucleophilic attack. Let's go to the next step. Next step is a proton transfer. You see that we have a proton on the oxygen here, but now it's only got 1 proton. Here it had 2. So who's going to grab that proton? Well, you notice, if you're keen, you probably notice that you've got water here, but then you've got hydronium here. How do you convert the water into hydronium? It's going to have to do a proton transfer. So we're going to grab a proton like this. So the water is going to do the proton transfer. We're going to break this bond, put the pair of electrons on the oxygen like that, a proton transfer. Now we're going down. So we're on this step going in this direction like that. And what's happening here? We have a nitrogen with 1 hydrogen to it. Now it's got 2 hydrogens. So this must be another proton transfer. How are we going to do it? Well, we're making a bond between a nitrogen and hydrogen. Where do those electrons come from? They come from, excuse me, this lone pair. So we're going to grab a proton from our hydronium, which is a strong acid. Then we're going to break this bond and put the lone pair back on the oxygen to reform water. And we end up with this intermediate. All right, something really interesting is happening in this step right here. I know that everybody tried these problems before coming to class today. Could anybody tell me what's happening in this step? Is it a proton transfer, rearrangement, loss of leaving group, nucleophilic attack? Anybody able to figure out what's going on in this step? Anyone? Not a proton transfer. This one would be a loss of a leaving group. We're losing a leaving group here, right? We've got a good leaving group here, and you see that we're breaking this bond, right? If you count from here, 1, 2, 3, 4, 5 at the nitrogen, you have 1, 2, 3, 4, 5 at the nitrogen. So that means you broke the bond between the nitrogen and this carbon that I'm highlighting in yellow right now, the carbon that's attached to the oxygen. Well, how does that happen? Let's take a look. What's happening is that we're breaking this bond, put the lone pair on the nitrogen, and then we're forming a double bond between the oxygen and the carbon. Well, where's that going to come from? It comes from these electrons right here. So this would be the loss of a leaving group. So we've lost our leaving group, and then what's going to happen in the next step is another proton transfer where we need to remove the proton from this oxonium to render it uncharged. And so the water is going to grab that proton. We're going to put the pair of electrons back on the oxygen, put them here, and that's it. There we go. We figured out every step in this mechanism. We've got what? 3 proton transfers, a nucleophilic attack, and a loss of leaving group. Again, it's one of those things you've got to practice over and over to get the hang of it. Any questions about that one? And again, don't hesitate to stop me. I have no qualms about stopping and rehashing chemistry. In fact, in case you never noticed, I can kind of ramble on about chemistry for quite a while. Okay, let's try another one. This one here I thought was kind of interesting. Um, it's an example of where you lose nitrogen gas, right? This is just plain old N2 gas. So let's see if we can connect some dots here and come up with a mechanism, because this one is not simple. We have, excuse me, excuse me, hydroxide, and we're losing this proton. So this must be a proton transfer, right? We're transferring this proton that I have in the black circle, and it's gone. So it must be a proton transfer of some sort. Well, let's draw an arrow from our base, our hydroxide. I'll put in the lone pairs. Let's draw an arrow from our hydroxide, which can abstract the proton. Well, where is this pair of electrons going to go? You can see that I have a pi bond over here. So I'm going to take those electrons and make that pi bond. Now keep in mind, the nitrogen already has 3 bonds in one lone pair. And here it's got 3 bonds in one lone pair. That means we're going to have to break this pi bond as well. So now we're going to take this pi bond and we're going to make this pi bond. But then that would give this carbon 4 bonds. That's impossible. So then you see that you have an oxygen with a negative charge. Well, where does that come from? The oxygen has 2 bonds and 2 lone pairs here, but here it has 1 bond and 3 lone pairs. Therefore, we're going to break this bond and put the electrons on the oxygen. So that's a proton transfer with 4 curved arrows in order to get the whole thing, correct. And we can see that in the next step, it must be the loss of a leaving group, because we're losing nitrogen and we're losing chloride. We're losing 2 things in this step. So what's happening here? You can see that we're reforming a carbonyl. Well, how do we do that? We'd have to take a pair of electrons from here and make the pi bond like that. But we know that carbon cannot have 5 bonds. This carbon would have 5 bonds if I was to just stop there. But you notice that we've got a triple bond. And so I'm going to break this bond because we no longer have a ring, and I'll make my triple bond. But then if I did that, this carbon would have 5 bonds. So what does that mean? I'm going to break this bond and put a pair of electrons between the 2 nitrogens to make that triple bond. But then this nitrogen would exceed an octet of electrons. And so I'm going to make the chloride leave like that. Chloride is the conjugate base of HCl, which is a strong acid. And there you have it. So this is a little more complex in that there's 4 curved arrows in each step. But in the end, all these both represent is first a proton transfer, followed by the loss of a leaving group. Excuse me. All right. And then this one, I'm going to skip this one. I mean, I don't think I would ask this one. I'm going to leave this one as an FYI for my students to see if you want to try to figure this out. You can see that the first step is just a nucleophilic attack of the hydroxide, right, which is a strong nucleophile. So we have the negative charge here, and you can see that you're doing a nucleophilic attack on this carbon right here to make this tetrahedral carbon. And then it's undergoing some kind of rearrangement here, it's not a rearrangement, it's a loss of leaving group because we're losing 2 groups here. But you could take some time to see if you could draw the curved arrows for this one. It's not as easy as some of the other ones that we looked at. It's a little more complex, but the same rationale still applies. So what I would recommend is that you go into the Chapter 6 module in our Canvas shell. And if you look at the Chapter 6 module, you'll see that I posted suggested practice problems. So suggested practice problems. And if you go into our book, at the end of chapter, he has a bunch of good questions where you get to practice drawing curved arrows. Because again, it's one of those things where you could watch me draw these arrows all day long, but until you try it, you will not master it. And so when you're practicing, if you have any questions, don't hesitate to reach out to me, and I'd be happy to answer any questions that you have about curved arrows.